Okay, so in the last lecture, we saw that if you have a circular region where the magnetic field is fluctuating, so maybe the magnetic field points into the page and it's fluctuating. Let's say it's getting stronger. Then this fluctuating magnetic field will produce an electric field, and the electric field lines will form closed circular loops. We can also figure out the direction of the electric field. So that we can just find from Lenz's law. So there is a magnetic field so if you consider any of these loops, uh, uh, just imagine having a wire. Let's just put a wire there. So let's have a circular wire here. The red circle is a circular wire. So these electric fields would send a current through the wire, right? And since from what we've learned about Lenz's law, we can easily figure out the direction of the current EMF, and that's the direction of the electric fields. Let's just do that as an exercise. So the loop sees that the magnetic field pointed into the page is getting stronger, so it will try to the flux due to the magnetic field pointed into the page is getting stronger. So it will try to counteract that by making its own magnetic field point in the opposite direction. So in order to produce a magnetic field which points out of the board, the current would have to be sent in this counterclockwise direction from the right hand rule. And so there will be a counterclockwise EMF produced if there's a magnetic field pointed into the board that's getting stronger. And so from there we can deduce that the electric field lines that are produced, the induced electric field lines, I'll draw another concentric circle here, though this is getting really cluttered. The induced electric field lines are going to look like this, with the electric field pointing the electric field in the counterclockwise sense, right? So we saw that whenever there is a fluctuating magnetic field, electric fields are produced. And when you have a nice symmetrical situation like this with circular symmetry, like the one that we are looking at here, the electric field lines are going to be closed circles. If you don't have circular symmetry, the electric field lines will just be closed loops, but not necessarily circles. Okay, so fluctuating magnetic fields produce electric fields, and these electric fields can drive an EMF and cause a current through a loop, right? Okay, now what would happen if instead of putting a loop over here, let me just clarify one more point. It should be fairly obvious. Suppose you have that region where the magnetic field is getting stronger again. So you have a region of magnetic field that's getting stronger. Suppose you have no loop here, right? So in that case, what would happen? You just have empty space, a region of empty space where the magnetic field is getting stronger. Would you have electric fields there? Absolutely. The induced electric fields would certainly be produced, but they would just have nothing to do. They would just show up, but they wouldn't have anything to do, no charges to push around. So they would just exist like this. So there would be electric fields, but you wouldn't have anything to detect them by, right? Whereas if you place a loop like we have in the other figure, this red circle is our loop of wire, then those electric fields will find something to do, and they'll push on the electrons in the loop of wire and produce an EMF in that loop. Okay, now let's look at the other extreme. Suppose you have a region where the you have this region where the magnetic field is getting stronger, and instead of having a loop of wire, let's say that you've placed a big chunk of metal. So the magnetic field is fluctuating over a big piece of metal, over a metallic conductor, right? Or any conductor, not necessarily metallic. So you have region of fluctuating magnetic field over a conductor, what's going to happen? So now the electric fields have plenty of charge carriers to push around, right? So what's going to happen is you're going to have loops of current. So you're going to have circular electric fields, and they will produce their own loops of current. Over here. So you'll have plenty of loops of current in this region, right? Now, typically, the region of magnetic field will not have circular symmetry. So if in general you just have a certain closed loop, I mean, if you just have a conductor and you're fluctuating a magnetic field over that conductor, then the induced electric fields will produce their own loops of current of various shapes and sizes. So there'll be plenty of loops of current of various shapes and sizes produced in the region where the magnetic field is fluctuating. These loops of current are called eddy currents. And what's the effect of eddy currents being produced in a metallic conductor? Any kind of current produces heat, right? And so these eddy currents are going to be strong currents because the resistance is very low inside the metal, and so they will generate a lot of heat. So eddy currents are usually, they have some uses, but they are usually a nuisance because they generate a lot of heat. Okay, now there is one other way in which eddy currents could be produced, and I'll just quickly describe that. Recall that in the last lecture we talked about how there are two mechanisms in which behind the induced EMF, right? One is the induced EMF can be caused by magnetic forces when you have a conductor moving through a magnetic field, right? That can cause an induced EMF, and we talked about that. The second mechanism is if the conductor is at rest, but the magnetic field is fluctuating over the conductor, then the fluctuating magnetic field produces an electric field, and that electric field is what drives the EMF. That's just what we have discussed today. So these are the two ways in which induced EMF is produced, right? So we just talked about eddy currents right now. There are exactly the same two mechanisms can also explain eddy currents, because eddy currents are basically just induced EMFs, right? They're caused by induced EMFs. So there is also another way in which eddy currents can be produced, and that is the following. So there is, I'll just go to the PowerPoint slide and show you. So if you have a conductor like this metallic wheel that's rotating in a magnetic field, so the magnetic field is confined to this blue circle. So that's the only place where you have a magnetic field. The magnetic field is steady in this case, but the wheel is rotating in the magnetic field. So in that case, you will again get eddy currents. And let me just quickly explain why that happens. Actually, if you just stare at this diagram, you'll be able to explain it yourself, but I'll just quickly explain it. That's the second way in which you can have eddy currents. So let's draw this figure here. So you have a wheel that's rotating through a magnetic field, and the magnetic field is just concentrated in this region. Actually, I should probably draw a larger figure. You draw a larger wheel, and there is a region of magnetic field, and the magnetic field is right here in this blue circle. All right, so this wheel is rotating. Let's say it's rotating like that in the counterclockwise direction. Okay, now consider an electron That's just sitting over here. The electron has no reason to move by itself. It's just moving because the wheel is rotating, right? So it's just imagine that this electron is sitting in place. What happens when the electron is passing, when this particular electron is passing through the magnetic field? So when it's passing through the magnetic field, it feels a force, right? Because you have a charged particle moving through a magnetic field. Chapter 27. What is the direction of the force? You can easily figure it out using the right hand rule. Index finger in the direction of the velocity of the particle, which is to the right. Middle finger in the direction of the magnetic field, which is into the page. And the force will be in the direction into your thumb. So that means there will be a force acting downwards on the electron while it's passing through the magnetic field, which will push the electron down, right? So our electron will move down over here. Another electron will from over here, and that will happen to all the electrons over here. So you'll have a bunch of electrons which are being pushed down. Oops. I'll draw the electrons in green, the forces on the electrons in green. So you'll have a bunch of electrons being pushed down over here. And so that's going to cause electrons from this region to sort of move in. So you'll have a bunch of electrons moving in, right? And that, yeah, so when that happens, then the next moment, these electrons which have been pushed down, they will move out of the magnetic field. So they will be somewhere over here, and they'll be saying, what are we doing over here, cooped up with other electrons? There's all this space if we go up a little bit. So those electrons will now want to go up over here where there's more room. So you can see that there is a cycle of electrons circulating like this, just because the wheel is rotating through a magnetic field. So you're going to have a circulation of charge carriers in this region. So basically that means the current will be flowing in the opposite direction, and you can easily see the same kind of thing would happen over here too, right? So you would have a bunch of these circular current loops forming because of the motion of the metal through a magnetic field. So this is also another example of an eddy current. So eddy currents can be produced both ways. Eddy currents can be produced because a magnetic field is fluctuating over a metal, and the induced electric fields produce the eddy current. Or they could also be produced because a conductor is moving through a magnetic field, a steady magnetic field, and in that case the Lorentz force on the charge carriers in the conductor cause eddy currents, right? Okay, eddy currents have many applications. So let me talk about a few of the applications. So one striking example is this one. So there is a rapidly fluctuating magnetic field in the coil, and the person passes a knife through it, and you can see how much the knife heats up. Why does it heat up that much? Because when you put the metallic knife inside the magnetic field, the rapidly fluctuating magnetic field induces electric fields, and those electric fields cause eddy currents inside the knife, and those eddy currents heat up the knife. All right, let's look at another example. There is an example that's very similar to what we just showed you, what we just discussed. So let's quickly go back to, actually I can just show you this figure. So looking at this figure over here, can you think of an application, a practical application of this? So you have a wheel, a metallic wheel rotating, and part of that wheel is passing through a magnetic field. It's rotating through a magnetic field. what would be a practical application of this? Well, one very interesting application, very clever application, would be a braking mechanism, right? So, and in fact, this particular mechanism is used for braking in many trains, because trains often have metallic wheels. So all you have to do is make that metallic wheel pass through a magnetic field, and that magnetic field will produce eddy currents. Eddy currents generate heat because they're electric currents, right? But where is the energy for that heat coming from? It's coming from the kinetic energy of rotation of the wheel. So the wheel will lose its kinetic energy and slow down. So this is a very common braking mechanism. And in the next slide, I have this video. Uh, so it's this eddy current brakes. So I'd recommend that you watch this video yourself. It's very interesting. I'm going to show you some demonstrations which I did for you guys. I would have shown these in class, but that's not an option now. So I went down to Vanderbilt and I recorded myself on my iPhone doing these demonstrations. And it's a good thing that I did them the day that I did, because the very next day, the entire campus was shut down and everybody was ordered to leave the campus. So anyway, so here is the first one that I wanted to show you. Not quite this one. Whoops. Okay. All right. So this is the podium in our classroom. I mean the table in our classroom. And you will not be able to hear the audio through this, but uh, if you play this video on your own computer, you would hear my fantastic narration. So anyway, so what's happening here is that there is a magnetic field and I'm swinging this piece of plastic through the magnetic field. Obviously, nothing happens, it just swings for a while. But suppose I bring this aluminium pendulum. I have got aluminium and copper, and I'm just showing here that aluminium is not magnetic, as you know. So I'm going to swing this aluminium pendulum through the region of magnetic field. Right? So let's see what happens. Do you see how quickly it comes to a stop? And for good measure, I show you how what happens if I swing it outside of the magnetic field, and you see that it swings for a really long time. It's got a large moment of inertia, so it just swings for a very long time. But inside the magnetic field, it does not swing for long at all. In fact, it comes to a stop rather abruptly, and that is because of the eddy currents, the kinetic energy going into the heat of the eddy currents. And here is a copper pendulum, same thing. It just swings for a long time when it's outside of the magnetic field. But in the magnetic field, it swings for a very short amount of time. Okay. Now, there is one other thing that I illustrate in this demo. One way of cutting down on eddy currents, because sometimes eddy currents can be a nuisance. So one way of cutting down on eddy currents is to make these grooves in a device. So if you make a bunch of grooves, then it's a bit harder for the eddy current loops to form because there are all these breaks in the material. So this copper pendulum has a bunch of grooves cut into it, which make it a little bit harder for the eddy currents to form. And as you can see, this one, it does not have that much damping from eddy currents. So this one can swing quite a bit. There's a little bit of damping because you do have some eddy currents forming, but the majority of the eddy currents are cut out because you have all these grooves, so they can't form. Okay, I'm going to show you another demo, which is an aluminium tube falling through a magnet. So I'm going to pause this video for a moment and let you think about this set this up for you. So basically, what we are doing here is we have okay. Before we talk about the aluminum tube, suppose I have a piece of wire which is made into a loop, right? And I bring a magnet like this. I bring a magnet and have the North Pole and the South Pole like this. All right. Now suppose I bring this, let this magnet fall, right? Or bring this magnet closer to the loop. What's going to happen? Now you can very easily answer this question. We've talked about this kind of stuff a lot. So the loop will see that there is a magnetic field which is getting stronger, or so the flux over the loop will keep increasing. The loop will want to fight that increasing flux, and so it will create a magnetic field. So the loop sees that a magnetic field pointed into the loop is getting stronger as the magnet approaches, right? So the loop wants to make its own magnetic field fight the increasing magnetic field. So it will send a current. The loop will try to send a current in the in this direction so that its magnetic field points upwards, right? And that will try to cancel out some of the increasing magnetic field, right? So if you have a loop that's driving current this way, then it will have a magnetic field pointing upwards, right? A magnetic field pointing upwards is equivalent to a little bar magnet with its north pole over here and south pole over here, because that would also produce a magnetic field pointing upwards, right? So in effect, the loop is acting like a small magnet which repels the incoming magnet. That makes sense? So the loop is going to act like a small magnet as a result of the current produced in the loop. The loop is going to act like a small magnet which repels the incoming magnet. So what's going to happen to the incoming magnet? It will slow down, right? Because of the repulsion from the loop, the magnetic repulsion from the loop. So now suppose you have, instead of one loop, you have a series of loops, one after the other. You let this magnet fall through the series of loops. So now the same thing is going to happen with all of these loops, right? So there will be induced currents in all of these loops, which will all act like little magnets, which are repelling the incoming magnet, right? So if you have a series of loops like this, then this incoming magnet will be slowed down quite a bit. What if you have, instead of a series of loops, what if you had an aluminium rod, right? Aluminium is a good conductor, though it's not magnetic at all. So now if you let a little magnet drop through this aluminium tube, there will be plenty of eddy currents which will form loops. So now you don't have a bunch of loops. So you can think of this aluminium rod like an infinite number of loops, aluminium tube like an infinite number of loops. So you'll have plenty of eddy currents which will just form inside the loop, and they will repel the magnet which is trying to fall through the tube, right? So now let's take a look at the video. So I have the aluminium tube, and I first take something that's not magnetic, and I'm just showing you that it's not magnetic. Okay. Now I drop the object that's not magnetic through the loop, and let's see what happens. It just falls right down to the ground. Okay. So nothing surprising there, right? But it gives you an idea of how much time it takes an object to fall through the tube. Now I take a magnet, and the magnet has absolutely no attraction to the aluminium, obviously. In fact, if I hold it, I just showed you that it has absolutely no attraction to the aluminium at all. So now if you drop this magnet through the tube, what happens? Let's see. I'm talking a lot over there. I don't know what exactly I'm saying, but okay. All right, so now watch. It's falling, falling, still falling, still falling, and finally it falls out of the tube. I'm going to do it one more time. Falling, 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 still falling, and finally it gets out of the tube. So it takes a very long time to fall through the tube, and hopefully the reason for that is clear to you now. Okay, I'm going to show you one more demonstration. Let me explain that. Suppose you have a solenoid, right? So suppose you have, so this is the next demonstration. You have a solenoid, and you pass a current through this solenoid. So let's say you pass an alternating current through this solenoid, right? So that means an alternating current is usually, this is the symbol for an alternating current. So if you pass an alternating current through the solenoid, that means the current is fluctuating, right? It's sinusoidally, and the so the magnetic field of each of these turns of wire is also fluctuating, right? Because the current is fluctuating, and so there's a fluctuating magnetic field inside the solenoid, right? In the region around the solenoid. Okay. Now, it's not in the region around the solenoid. Sorry, inside the solenoid, you have a fluctuating magnetic field, right? Okay. Now, what happens if you place a loop surrounding this fluctuating magnetic field? So, what? Suppose the magnetic field is increasing, right? Then the loop will see that there is a flux caused by a magnetic field pointed upwards getting stronger. So the loop will try to make its own magnetic field uh, point in the opposite direction, right? And so the loop will send current in such a way. So if there's a magnetic field pointed upwards here, that's getting stronger as the current is increasing, the loop will send current in such a way that it will produce its own magnetic field, which is in the opposite direction, right? So basically what's going to happen is that the magnetic field induced in the loop will be opposite to the magnetic field that's produced inside the solenoid, right? And so there will be a repulsion between the solenoid and the loop. And if the loop is free to move, that magnetic repulsion might cause it to jump up, right? And that's what I want to show you. So let's take a look at that. Okay, so um, this that is the solenoid, right? And it's connected to the mains. Okay. So uh, okay, I've forgotten what I was talking about. Okay, but anyway, so I place the ring over there, and now I'm going to send a current through the solenoid, and you can see how it jumps up, right? Okay, I try that with a different ring, copper. That also jumps up. And then this is one more, brass, that also jumps up. Notice that none of these things materials are magnetic. The last one that I'm going to show you has cut in it. So if there's a cut in it, you should be able to predict what's going to happen if there's a cut in it and nothing happens. And that is because those currents cannot form if there is a cut in it. Okay, now let me explain this. So I'll come back to this. Now for the next demonstration, I have the solenoid as usual. And I'm surrounding it. So there's a fluctuating magnetic field inside the solenoid. And I'm surrounding the solenoid by loop of wire. And this loop of wire is connected to a light bulb. So the light bulb will obviously light up whenever there's a current flowing through that loop, right? And there is no electrical connection between the solenoid and the loop of wire connected to the light bulb, right? So there's absolutely no electrical connection here. Actually, in the demonstration that I show you, this is not really a single loop of wire, but this is also another solenoid. So this has a few turns of its own. That is just to magnify the effect. Okay, so let's take a look at that. So I have the solenoid connected to a light bulb, and I'm holding it right there. I turn on the fluctuating magnetic field in the large solenoid, and you can see how the light bulb lights up. So I think that's pretty amazing. I mean, I still find it pretty amazing that it lights up and there's absolutely no magnetic field. I mean, absolutely no electrical connection. It's all via magnetic field. Okay, so those are the demonstrations. Now, there are other many fascinating consequences of eddy currents. One really fascinating application of eddy currents is a metal detector. So how does the metal detector work? So suppose this is a metal detector, standard metal detector in an airport. So the way this one, what happens over here is that there are two large coils, one on the left over here and another on the right. One of them is called the transmitting coil and the other one is called the receiving coil, right? So as the person is standing inside the metal detector, a fluctuating current is sent through, a current pulse basically is sent through the transmitting coil. So this fluctuating current produces a magnetic field, a fluctuating magnetic field. If there is anything metallic on the person or in his suitcase, then that fluctuating magnetic field will produce an eddy current inside the metallic object, right? Now, eddy currents are fluctuating currents. So those fluctuating currents, eddy currents, will produce their own magnetic field, right? And the receiving coil will feel not only the magnetic field due to the transmitting coil, it will also sense the magnetic fields produced by the eddy currents inside the metallic object, right? So if the receiving coil simply picks up the same signal that was produced by the transmitting coil, then you know that there is nothing metallic. But if it picks up anything different, then you know that there are metallic objects inside the carried by the person or in his property, in his belongings. So that is how metal detectors work. Now, I want to show you something else. The planet Jupiter has how many moons? Take a guess. The answer is about 67. So it's got 67 moons, and 4 of those moons are the most prominent. They're called the Galilean moons. Right? They have really interesting properties, and they're called Galilean moons because they were first seen by Galileo almost 400, a little over 400 years ago. In 1610, Galileo was looking at the planet Jupiter through his rudimentary telescope, and he was amazed to see these spots of light orbiting Jupiter, and he figured out very quickly that they must be moons of Jupiter. So the closest Galilean moon to Jupiter is Io, right? Um, when one of the Voyager spacecraft flew past Io, uh, they were and sent us some pictures of Io. The scientists were just amazed to find that the surface of Io has this really strange color, yellowish color. Not only that, there are active volcanoes going on Io. So in fact, Io is the most volcanic place in the entire solar system. There's constant volcanic activity going on in Io. And over here, you have this is an active volcano on Io. This picture was taken by, I think, I've forgotten which spacecraft took this picture, but it's so large that you can see it from space, right? Uh, the volcanoes on Io are nothing like the volcanoes on Earth. So on Earth, you have the lava coming out very, very slowly and then just oozing out of the volcano. But in Io, you have super hot lava which just shoots out into space at very high velocities. This picture right here, yeah, this is an amazing picture. You can see the surface of Io, how it looks so yellow. And right here, you have a volcanic plume, an 86-mile volcanic plume. 86 miles. Can you imagine an 86-mile plume of volcanic material? Um, just unbelievable. So, uh, so Io is a very, very, very highly volcanically active region. So now the question arises, why is Io so volcanic? And where does it get its energy for all this volcanism? So where does all that energy come from? Well, there are two explanations. There are not two explanations. There are two sources of energy that scientists believe cause the volcanism of Io. One of them is due to something called tidal flexing, which I never have time to explain when I'm discussing this in class because I'm just rushing to finish the material. So, okay, I'm not going to talk about it now. But that's the most important source of heating uh, on Io. The second source of heating that causes all this volcanic activity is eddy currents. So where did eddy currents come from in Io? Well, Jupiter has a tremendously strong magnetic field, extremely, extremely strong magnetic field. Jupiter's magnetic field is like 20,000 times stronger than the Earth's magnetic field. So as Io flies through Jupiter at 60,000 kilometers per hour, I mean, flies past Jupiter at 60,000 kilometers per hour through its magnetic field, uh, there is believed to be a lot of magnetic minerals, magnetic materials in the crust of Io, right? And the eddy currents caused by Io moving through Jupiter's magnetic field, so rapidly moving through Jupiter's magnetic field, uh, causes Io to heat up. So Io's volcanism is caused by the eddy currents, which are the result of its motion through uh, Jupiter's magnetic field. But that is the second most important reason. The most important reason is called tidal flexing, which we really don't have time to discuss. Okay.